when I go to high tech, there's always kind of R&D type programs, but when we talk about Slender columns to the National Science Foundation, unfortunately, they don't think it's sexy. They think we already know how to build high rises, we know how to do everything. Why would I fund research in this area? So I really appreciate the support. We had the Concrete Industry Foundation in New York, so thank you very much. Concrete Research Council, which is through the ACI Foundation, they also contributed. The Concrete Reinforcing Steel Institute, Mike Moto was very instrumental, also making connections here with CIF. And then also the Precast Pre-Stressed Concrete Institute, because it turns out Slender columns are commonly used in pre-stressed concrete, but the provisions are non-existent. The code really doesn't address pre-stress, so they were interested in that aspect. So let me talk a little bit, and I know we have a very group of different backgrounds here, so hopefully I can delve into some details, but also give you a kind of an overall perspective if you're not a structural engineer. Columns, when we generally talk, especially at an undergrad level, we talk about really these short columns or stocky columns because we don't have to worry about one major thing called slenderness or second order effects. The second order effect is additional forces that develop because of the bending of that member. So in a first order, we just look at actually the forces in this member. But with second order, we have to consider the fact that it's bending, and that bending is going to cause extra forces. So this goes back to a guy named Euler that was looking at buckling. And the equations actually elastically were very simple. When I say very simple, they're not that difficult to really comprehend. The only thing that was complex for some is it added pi in there, and the students were sort of, how do you get pi inside of an equation? But when I look at this, the problem with concrete, steel, it's much easier because there's an E that I work with. But in concrete, we have cracking and a modulus that's not as consistent and constant. So because of this, we also pick up something called creep. And creep will have second order effects. So I don't have that issue with steel where I'm shortening as I go. So those are some of the complex pieces. And one other thing just to mention about cracking, it's not just uniform cracking. Where there's higher forces, you get increased cracking and decreased cracking at other locations. So there's varied amounts of cracking throughout the member. And then what's happening right now is new materials. And this is not just something that happened today. I mean, we're looking at high-strength concretes that are approaching 15,000 readily used in construction, approaching 20 in some markets. So now with higher strength, we can decrease the size of the column, and then we go into the steel, and I saw we have some high-strength steel folks in the audience. Grade hundreds, I worked with Pankow Foundation, and we're trying to look at how we use grade 100, maybe 120 KSI, and when we do those type of materials, that could also shrink the size of these columns and have more leasable square footage for developers, things like that. So there's definitely some interest in this area. Now, it depends on the part of the country I'm in. Here, I think you have more interest in slender columns. When I go to California, they're like, well, it's seismic. I'm really not so interested in the slenderness aspect. But let's look at a typical column behavior. So this is kind of classroom where I'm looking at the axial load on this vertical axis, and I'm looking at how much bending moment is on the horizontal. So we typically, in a code type fashion, we develop this interaction curve for the axial load, and this is the column capacity at nominal strength, so what it could actually take. If I have a short column, and I would load it up, and so I start here, zero load, and I start loading, and as I load, if I have some moment on there, it's going to linearly increase, and I get this straight line until I hit capacity. And that's what we teach in an introductory structural concrete class to students. I want to stay inside of this range because outside it will fail, inside I'm good. As I continue to increase, because of the bending, it is second order effects, and it produces more moment than what I have for the same load. So if I'm at this load level, I actually have an increased amount of moment I need to resist. And what that results is, ultimately when I hit the curve, I'm going to hit it lower, and I have a reduced capacity because of the slenderness. The capacity of the concrete is still the same. It's a matter of, I actually have increased moment I have to resist. So one other problem though is, that would be great if I'm just loading up, but we often bring loads up to a certain value and sustain them for many years. And so that's the sustained load effect. If it came over here and sustained and hit the curve, that's often known as creep buckling. We don't want that in our buildings where I'm at a load and all of a sudden it just over time continues to deflect and then it fails. So normally we're going to have it where we want to stop it at some point, be safe inside, and that means there's some residual capacity once I would actually load it. So if I had some additional loads on top, it could get there. Let me talk a little bit about design in ACI. 318 allows 3 different methods of design for these slender columns. There's nonlinear second order analysis. This is the most complex. And actually, if you look at the code, and I work, I've been on the code for a while. 318.14 is a complete new revision and has that. I'm going to reference right now because I know a lot of places are still using the older code. So I'm not going to talk about the 14 in terms of numbers, and I will talk about what 11 has. But I love to read the provision about this to my students because it tells you in there as an engineer you have to account for everything. Settlement of the foundation, creep, and shrinkage, and it's kind of my favorite passage. If you can do that, you can do anything, right? It's just one code provision. It actually was written by Jack Breen and Jim McGregor back in the 71 building code. They actually were thinking about this back in 71. They said, and I was taught by Jack Breen at University of Texas, Austin. He said, we saw computers coming in, we knew we could do that in a few years. Well, here we are today, and it's questionable whether we can fully do that, although there's some tools out there that do much better on the nonlinear second order analysis. Elastic second order analysis, the computer programs are there, that's what's rarely being done today in the office. And then there's moment magnification procedures where I do an elastic analysis, I take a magnifier to increase those moments. So if I have global second order in a frame, I get a deflection laterally here, and this is the big P delta. So P big delta. So we're getting second order effects from that sway of the frame. Elastic second order analysis picks that up. Great, right? You have most programs default to that now. You can put a checkbox on some that will run that, and so you get those forces. The program is giving you the forces at the end of the member. So I'm going to pick up whatever that second order effect is. The problem is these programs don't pick up the P little delta, which is magnification occurs between the ends. And if you look at SAP 2000 or one of these programs and you read their manual, they're going to tell you the best way to do it, in which the ACI code's telling you to do it, use the moment magnification procedure. Because what happens is if you want to do this, otherwise you need to put nodes in between the ends of all your columns. Also, the EI that yours recommended by the code to use is different EI than the overall frame. So the P little delta is really still a hand procedure that needs to be done here. And so this is the way to do it, reduce computational cost, obviously if you're not having to put nodes everywhere. Let me talk about this procedure. It's based on elastic stability analysis. Timoshenko, if you go back and look at some of that, this is very classical type work. General method that we're going to talk about, what's in the code today, has remained unchanged. It turns out that's a great method. I mean, that's how it works. There's a simple equation that's looking at small deflection theory. It doesn't mean that they're that small, but small deflections, it assumes a shape, a sine wave for the deflected shape, and it actually hits, unless you're right near the buckling load, the answers perfectly. I mean, they're very good. So it's a sound theory, and we take the moment that we get out of the analysis, and we're going to amplify it with this magnifier delta non-sway. So I'm looking between the ends, that's the non-sway multiplier. The sway multiplier, if you were looking at that, is only at the end. This multiplier, classically, it's 1 over 1 minus P over P critical. It'll look a little different here. C sub M is if I have different moments at the end. It's just giving me a uniform moment that I use into my equation. And then the code puts a 3/4, a phi factor, if you will, on stiffness, because if the column's not built exactly right, the stiffness will be lower, and we want to make sure we're safe here, and when we're looking at the total buckling load that the column can. But this little 1 over 1 minus P over P critical is actually a very simple equation to magnify with, and that thing is darn good. I mean, if you go up and look at it, when you're about 80-90% from the buckling load, that's where it starts diverging from the theoretical solution. But from where we're needing to design, it's almost perfect. This relies, though, as I mentioned earlier, on the EI. What's the EI? And for concrete, if I'm steel, it's easy. If I'm concrete, the problem is what's the E, right? I use an equation like 57 root F prime C. I, I could use gross I could use, what do I use? Because it's going to be very cracking throughout the length. So the code actually, going back 71, there was some great thought into this. They have a provision that says it's 0.2 EI gross, so make it simple for designers. And then there was something to account for how much steel you have in the section. So it's the I of that steel times its E. Or you could just use 0.4 EI. And so most people I know just go to this because that's really simpler than having to calculate. You don't even know the steel when you start to design in the section. So 0.4 EI, go to town with it. So that's traditionally what's used. And if you look at how these do, this is the theoretical EI relative to the EI from the equation. So if you go to the theoretical, you'll notice here, depending on the axial load level, they're showing a 1% and an 8% column. Those are the bounds of what the code allows. 1% minimum, 8% max. So as I'm looking here, it says this equation at 8% actually does really good. I mean, it's almost perfect. But if I'm actually at 1%, I may be off by a factor of 2 here. Now, interesting, the scales are not the same. This came out of the paper that was originally done on this. You'll see this EI. If I'm 1%, with this one, it actually works really good. If I'm 8%, there's a huge band. And it's off, but look at this. This is 1 to 5. I mean, so the range there is quite large. So we're not looking side-to-side comparison on scale. So we know they're not that accurate, but it's safe, right? 0.4 is going to be a safe value that was based upon the work. So there was a new equation that came out of essentially the task group. SK Ghosh had done some work that was sponsored by PCA, and there was a Kuntia and Ghosh equation that was developed. And this says, well, I could estimate the EI instead of by these, by this, which takes in how much steel I have and how much eccentricity of moment, axial load, and it'll do the job for you. The negative side is obviously it's fairly complex, right? And so I don't know anyone using this equation. I don't know anyone in the audience using that? I see one. All right.
I tried it and honestly you didn't like it, so I went back.
All right, went back 0.4, right? It's a nice number, right? So long-term column stiffness. So that's the short term, that's the EI, but then we have to account for creep. So that's the second aspect here. And so we have the sustained load ratio. So the way the code does is this EI over 1 plus a beta DNS. So basically we're taking EI dividing by some fraction. So we're going to cut it down. Like if I call this 1, that's going to cut it 50%. So I get a 50% EI. So the code does it right now by saying this PU sustained relative to the total PU that's on the column. And you know, that's the ratio. What's interesting, if you go back to original work, this wasn't even based on axial load, it was based upon the sustained moment. It wasn't the sustained axial load. And I actually asked Jack and them, well, why did we, where did that change? Because we can't even find a paper. And they said, well, it was easier for people to use the P than the M. We thought it was close enough. It kind of relates, and so that's kind of, it just happened. So there's not as much on it. Now also it's very interesting, the sustained load effect, it's based upon very limited experimental tests. There are only 11 tests from the 1960s that's based upon. So I think what's funny is I'm on the code committee right now. For us to get anything into code now, and there's an equation you want to pull out, man, where's the proof? We got to pull this out. Or where's all of the tests, the background for putting something new? This is slender columns that are major elements of a building. Yet it was based upon 11 tests, and these things were like 2 inch by 2 inch and 4 inch maximum size columns. So it's pretty interesting. This equation does not really consider creep, because creep is a function of the age of it, what's the stress level on the column. So one other thing is in 08, a limit on the second order effects came in and said that now we can only have 40% extra second order effect. So if you have more moment developing 1.4 or higher, you're not allowed to design it, you have to go back, okay? That was based upon this task group too. Really, the goal of that was to devise for global stability. It kind of ties back to the IBC, that there's an equation in there about lateral stability. We were getting rid of stability checks, so putting this in indirectly did a stability check on the lateral. The problem is it's also implemented for the non-sway. And so, do you need it? Because now there was no limit in the past, and actually designs, if you go look at like PCA notes, examples in there don't work anymore because they were using higher than 1.4 non-sways. So designs that would have worked in the past say now they wouldn't meet the code. One is to really improve the behavior, understanding. No one had really looked at slender columns anymore since really that time back in the 70s. Looking at both short-term and long-term effects. And then we wanted to develop some maybe improved design procedures for the moment magnification procedure. So we're looking at the non-sway, because this is where we really need to have this benefit, and address this limit on second order. Do we need it? Do we not? And then, like I mentioned, for PCI, they were very interested in the pre-stress columns. I am not going to focus the talk today on the pre-stress, just because of the nature of the time here. We'll focus on the cast-in-place construction. And then increase the efficiency of concrete columns, because you know, if we want to use these, we need to maintain reliability, but on the other side, remove barriers. If we're cutting our EI, in fact, the EIs can go down to only 0.2 EI, right? Because I'm going to take that 0.4 and cut by 2, and so when I do that, I'm down to 0.2 EI, and that may be really over penalizing where I have to have a much larger column anyway than I really need for the behavior. So first phase is we went analytically. And so the first phase of the study said, let's develop a model that can evaluate this, because this is just bending and axial load. We ought to be able to do that. So we looked at the stress strain for concrete using the regular Hognested relationship. If we go to high strength, we may use a little different, but Hognested works actually very well for even for higher strength materials. And then elastic plastic, very simple. We're looking at grade 60 was the focus of this work. Using moment curvature, standard analysis procedure, and then we use moment area to actually calculate deflections. So nothing that we, you know, tried to fit curves and just saying, look, let's use basic assumptions, see what we can do. So let me just show you what we can do. So this is the nominal capacity, we generate that. And this is the experimental curve. So it comes up load, you see the second order. If it would be no second order effects, it would just be a straight line up, but second order effects come over. And nice, you know, the capacity was predicted conservatively by the code. So that's good, that this is where it fails outside of that curve. This is what our analysis can do. So just using those regular assumptions, we can follow that curve and predict it very well. Here's another test. Again, outside, if you look, this one's in red with the lighting you may not see, but it falls right on top of the analysis. Here's another one, tested, it failed right at the curve. We actually get and follow that analysis. So using very simple moment curvature relationships, we can predict the behavior. This is short-term effects. So we estimated the failure load accurately. The load-moment relationship works out. We can do that. We did estimate with high eccentricity, so there's quite a bit of bending on those columns, a little more accurately than when we had very high with very little moment. We were maybe a little more divergent. And you can see that actually back here, a little divergent here. These were almost hitting right on top of the curve. We estimated frame behavior. There were some frame tests in there. We estimated that well. And then we really accounted for all parameters. I didn't care what the variation was, concrete strength, eccentricity. We could predict that. So that means our analysis tool works pretty well. And it's, again, not a contrived method. It's just using basic mechanics. Now, what we wanted to do, though, I mean, we could do that and write a software package. You could do that yourself. We don't have to write the package. You could just analyze it. But we want to look if we could come up with something that would be a code expression a little simpler. So we looked at the influence of all the parameters on stiffness, and we wanted to come up with like an effective stiffness. Realize the variation of cracking is different everywhere throughout that column, so we need to come up with one common EI that represents the entire column, and that's the challenge. So we back calculated what that EI would need to be to work. We started with just a control column that we would vary all kind of parameters and take a look. So this was just for the analysis. So we start with a 12 by 12 and then we ramp it up to all different sizes. But we had a basic control column, 5,000 PSI, 1%, which would be the minimum stiffness you would ever provide, a KL over R of 33, so not a little slender, not very slender, 60 KSI steel, and we start out with 5% eccentricity on the column. So now what we're going to do is push it in all types of directions. Okay, so basically the EI relative to the gross EI, as I load this thing, and so this would be very low eccentricity on it, not much bending. It starts to get softer as you approach the total load or the squash load of the column. P0 would be the total capacity of that column without any slenderness effects, okay? So it's like almost 85% F prime C, but that's including the steel and everything. What's the total squash load of the column? So you can see this, it's a little bit of a curve, but we could represent that with a very simple line across here and predict the stiffness at any axial load level. So from 1 to 8%. Now, I don't know how many people are designing out here. I don't think many of you are, because you can't hardly stick that steel in the column, right? At 8%, physically it just doesn't fit. You got to definitely use couplers if you're going to do something like that. You're not splicing anything. So between 1 and 4% is really where we're most interested, but we looked at the whole range. So it turns out with the monosteel, what actually you're seeing a range here that's happening. This is because we're looking all the way from low axial loads all the way to very high. So at the high or low axial load we're here, and as the axial load goes up, we may have a little bit of reduced stiffness, but we're picking this up across here. And so this little line could represent how much steel you have in a column. Again, from 1 to 4, I'm looking here, I can call it 1. I mean, I don't need to even use a line. I can call it 1 and there's no variation. If we want to account for it, we can. The eccentricity is another animal because as I have more bending, there's going to be more cracking on the column and there's more variation because if I have bending and a lot of axial load, I don't crack as much, but if I have low axial load and bending, I can get more cracking. And what's very interesting here is if you take a look at it here, up to about an eccentricity of 10%, you find out that there's really no effect of the eccentricity. As I'm coming into this zone, I actually have a decrease, and you see a big scatter range, about 25%. And that's where I'm looking at whether I actually have high axial loads in the column versus low axial loads in the column. It's going to change how much cracking is occurring within that extent of the column. And finally, when I get out to these high eccentricities, 45% or higher, the thing's fully cracked everywhere. The column's cracked. So it doesn't matter how much axial load you have. You got all of that cracked eye to work with. So we found out we could represent this in this dual banded range. Uncracked, we don't worry about the eccentricity up to 10%. And then if you were having some higher eccentricities, we could come down this transition zone, represent it, and then ultimately fully cracked. For analysis, so I'm going to say for analysis first. So if I really want to get, what's the best thing I could get at you, I would throw up this equation. So less than 1% eccentricity, I have a term for the axial load, I have a term here for the amount of steel, and I can predict the EI. Greater than 1, I have to add another term because I'm now going to have to account for the eccentricity. Again, as I mentioned, this term here, I can get rid of that. I can call it 1 and say, don't worry about how much steel I have. So we did that. And also, going back, this P0 was the squash load of the column. That's how much concrete can take plus the steel. But I don't even know how much steel I'm going to stick in a column to start with that I'm designing. So for design, we wanted to actually base it upon 85% AG F prime C. So forget the steel and base that P0, if you will, on that. When we did that, it actually just tweaked these coefficients a little to make that work properly, and it creates a very simple equation. So if I'm lower than 1% eccentricity, this would represent the EI of that column. And again, if I have higher, I have to take any eccentricity into account. This gave really improved accuracy. It maintains conservative results. We base it to be conservative. We use only original design values. Again, as I mentioned, we're trying not to think about, well, we don't know how much steel gets in it. So, you know, if I'm analyzing, that's one thing. But if I'm actually trying to design, I want something I don't have to know what the column is to start with. Except for, obviously, the brute size. I'm going to try a size and see if it works. And then, as I just mentioned, we conservatively ignore that reinforcement ratio. So analytically, let me say this. Now, once we had this figured out, we know we could predict with our analysis model any column in the world because we fully could analyze that. We looked at 288 different columns, all the way from 1 to 8%. We looked at 12-inch to 48-inch square columns. We were focused on the square here. And we looked at slender ratios to crazy 95. I mean, really slender type columns. We had lotus scenarios. We started at 0.1 of the axial at P0, the actual capacity of the column, and take it all the way up to failure. We also looked at eccentricities all the way from the 5 to 50%. 50%, I think, is a beam. I mean, it's huge eccentricity. This was 20,000 data points. We ran 20,000 essentially columns and simulated those tests. What I'm going to show you is how well ACI here does here versus what our design equation does. So the 0.4, just to give you an idea. So this is what we do with this equation. So this 1, anything 1 or higher is conservative. So this is how much moment that actually is developing versus what the analytical model is saying. So if I'm below 1, which I have just a couple points here, would say I'm unconservative with this approach. ACI 1015, which is the 0.4 EI, that's what it does. There's the red. So I think you can see it. We bring a little bit of complexity. I mean, it's not 0.4, right? But we account for what EI is actually in the column, and we can predict it very well, and it gives a very safe procedure. We have greater than 2 on some of these. And that makes sense because I showed you before that it wasn't meant to be a perfect equation. Now, if we look at this compared to the one that is in the code, this is that complex equation. So again, here's us. And there's them. Actually, their equation's pretty good, but the problem with theirs, it turns out there's actually much more unconservative columns that can resolve. It over-predicts the EI in some instances. It depends on the column. So we don't like that to continue use in 318 because it can be unconservative. But I have another issue with it, and we'll talk about that. So analytically, there are three primary parameters on these columns. It's the axial load, the eccentricity ratio, and I put low as the reinforcement ratio. It has some effect, but we can just forget about it. I mean, for 1 to 4% columns, which is I think the bread and butter, I don't need to worry about that. The simple equations, they are conservative, so both equations in the code are clearly fine, so don't have any concerns about continued use, but they are inaccurate. The ACI complex equation, as I just mentioned, is accurate. I mean, that thing's pretty darn good, but there are unconservative results that develop, and so we are going to kind of reconsider this use in ACI 318. The proposed design equation is conservative, and yet we think fairly accurate. So you lose a little bit of accuracy, but I think it really tells the story of what's going on in these columns. So the final the phase of the project next was the phase 2 is experimental. We only had a certain number of columns to base our analytical off of because there was not a lot of columns out there. So we wanted to test more that tested the bounds. And so this is our loading setup. We have steel plates here, we have rods here, we can lock them down, sustain the load. We wanted to look at sustained load effects also. So we maintain idealized conditions to make it simple to compare. We looked at non-sway. This is a picture of the frame with the loading jacks here that we load, and then we lock the nuts down here to sustain load. We measured the displacement at the mid-span. So it's a fairly simple loading. We have pin ends. So we can put exactly the eccentricity. And for this, we wanted to compare to actual analysis. So we made the two ends the same eccentricity. We know the C sub m that's in the code works well. That's been validated. We wanted to understand the second order. And then we had, as I just mentioned, that equal eccentricity at the end. The parameters, these columns are 6 1/8 by 6 1/8. And so you might say, well, those are kind of small compared to what we're building. Well, unfortunately, the loads to fail these things go quite high. And so you're often limited to that and how long the column's going to be in the lab. And you'll see some of these are fairly long. So it would be nice to do bigger. It's just how many millions of pounds we have to put on them to fail them. This is a scale higher than what was done before, though. So we felt that at least these were realistic. Slender ratio is 40 and 70. You'll see some of this, the L over H ratios for those two. Concrete strength, we went with 6,000 to be kind of not at the high strength range, but also not just 4,000 regular, because if you're building some of these, I think we're looking at a little higher strength material. We went with 1.2 and 3.3 to bracket the lower and what we thought is more of a higher range, and eccentricities of 10 and 25%. So we think it's pretty practical. Here's some images of the lab when we're casting them. So these are the different columns, and you can see some, of course, you can see this relative to the cylinder there. You get a little bit of sense of scale. They're reasonably sized, and then we have our ties. So here's the bed there before. You'll also notice we did some short columns too. We calibrated some of our creep and shrinkage that's occurring relative to short columns that didn't have second order effects. And here's one of the columns, and this one is under sustained load at this, and you can see that displacement. You probably don't want that in your building, right? Or it could be interesting. That's our banana column, I don't know. Short-term results. So we loaded these up. This is axial load versus deflection. So you can see that load coming up. You see the second order effects. These are just different ratios. So these were all number 5 board tests that we did. So it would have been about 3.3%. This is the 40 ratio, kilobar 40. These are the 70s. And then 10% eccentricity, 25. You can see how the eccentricity plays a big role. How it drops down the capacity. The 70, obviously, slender, it means you're going to actually have much higher moments on these things, and then the deflection. So let's just look at the design equations I just mentioned before. This is the nominal strength curve. This is the design strength. So this is where ACI would bring us in with our fee factors for the safety. Experimental results, we're looking good. I mean, in all cases, our tests fail beyond what ACI would allow you for design past nominal. Okay. There's our computational model. So when I say the model again, there is no calibration of this model. This thing is just plugging in E of 57 root F prime C. It's plugging in, Hodgman state stress strain curve. We didn't tweak anything to make it fit. It is just using regular mechanics, and we can predict the second order effects, short-term loads perfectly. I mean, it was uncanny how well these things can predict. The analysis equation, I mentioned that one. This is a simplified equation that we developed. That's how well that does if we were to use that as our EI. And then the design, obviously we were conservative, right? We cut down that, and so it still does reasonably well because actually we're not really worried about predicting out at nominal. We're designing here, the PU is what we're trying to get, and all of them do pretty darn well right around that level. And there's 0.4 EI just for comparison. So, again, it's a conservative. I take nothing away. 1971, when they came up with what to do here, that's not a bad number. And there's the comparison. So we compared all these things just trying to understand. We actually had 43 columns additional to what we'd looked at before from our study. So Ryan Jenkins was my student, Penn State undergrad. He came to us. He actually was like their top student at Penn State. He had a 4.0 there, came to us at Purdue. He had a 4.0 through his master's with me and his PhD. So he's a stellar guy. He's living in Pittsburgh now. Just wrapped up his PhD on this project. And Lloyd Rangan did some 15 KSI concrete columns. So we like that to look at that. So here's our range from a low of 5,500 in our test to the 15s that were in Lloyd and Rangan. We had all kind of range in K/over R's and that. And so statistically, and I'm going to jump down to design strength, okay, which maybe you're interested in, design strength levels. You can see that our proposed equation gave very accurate 102, the standard deviation is 0.06. So it looks pretty good. You can look at comparison. The problem with Kunti I mentioned that's in the code, they kept, even at nominal and design, they're a little unconservative. And so we don't like that unconservative nature. And then you can see how the other ones do. Actually, the 0.4 standard deviation is not too bad. But really here, compared to even Kunti, our standard deviation is actually better. So, we feel confident that short term, we got it. This is a great equation to use. So, they do provide safe lower bounds. The Kuntia, I think, again, should unconservative. We're not that convinced with use of that furthermore. The equations that we have are more accurate, and I think those are good to move forward with. Long-term tests, whole other animal. Because I'm sustaining a creep, there's shrinkage going on too that interplays. We looked at all these different loading parameters each once. Okay, so we had a 0.1 and a 0.25 and the E/H. We did two slenderness ratios of 40 and 70. So 70 is pretty slender. We loaded for 100 days, so they were sustained for 100-day loads, which actually is more than what was originally done. The original ones were about 30-some days or so, so we sustained fairly long here. Applied normalized loads relative to the squash load, again, the P0 total load. You'll see here we had some different ratios, so we went about 40% here at the 40 ratio and 35% with higher. The higher moment, I can't load as much. And also at the 70, you really can't put much axial load on these things. You have to lower that load a lot that we can sustain under. And so there's where our sustained levels. And so what you see is a curve like this. This is the axial load versus deflection at midspan. You bring it up to the sustained load level and you sustain. So as you're sustaining, the load stays the same, but the deflection is going to increase on you over time. And you can see how much that deflection increased. So here, K/40, it was 3 times. Again, at 40, it was a 3-time deflection increase while it's just sitting there for 100 days. This one at 70, 4.5-time deflection, and then at 3.1. So we take that, we can convert that to moment, so you can put in a plot that you're used to seeing. Interesting enough, the deflections look much higher, but when you convert to moment, it turns out that they're not as significant, the jumps. They're 1.2, and then there's 2 and 1.4. And so you'll see the moment change is not as, because you have a first order deflection, and just look at the second order change, okay? So you'll see again, they all fail, even after sustained load beyond the nominal strength, which is great. That's what we want to see. But what we're trying to do is predict this. And it turns out, it is much more complicated than I first thought when we got into it. We can come up this line to here perfectly, The question is how to predict over time with that sustained load this extra, and then from there reload it again to get it up to failure. And again, it's not as easy as I originally thought we could do. So let's talk about the beta DNS method that's in the code. This equation is what we use because that was a little better than design. We were trying to figure out how to get there closer. So that's coming up here, and I mentioned it does pretty good. This is beta DNS is 0, meaning there is no sustained load effect. Short-term stiffness, there we go, and we fit. Reduced stiffness. So the code actually has a commentary that mentions I can just use 0.6. It doesn't matter what the loads are. I can kind of use 0.6 and it'll work out pretty well for you. So we looked at 0.6 as just a number because it's hard to figure out some of the other ratios. So if you do that, this actually 0.6 on that works pretty well, right? Design, and it's conservative here. So right there, we almost hit it with the 0.6. Let's look at another column. So here's the experimental test, and here you'll see the 0, again, analysis picks it up really well, that curve coming over. But at the design, this 0.6, you're going to see that we are basically not conservative. 0.6 is just not reducing enough stiffness for this column at the design level. Now when I get over to here to nominal, it's hitting it again. But the question is, when I'm calculating these, I'm really thinking about calculating them around this location. If I use a beta DNS of 1 no, I cut it down to 50% to account for the sustain effect. It works pretty well, and it turns out using 1 was generally conservative for all our tests. So we kind of like, if we want a simple number, 1, just cut it down 50% for the sustain effect. Using an accurate equation works reasonably well. Let me show you beta DNS here. This is using the 0.4. So 0.4 EI, again, it's going to be conservative by ACI. And then if you take the 0.6, which they're doing, you get way lower, in terms of that behavior. So again, conservative is safe, but if we want to really push Slender columns a little more to what their capacities are, we're really not able to make them as slender as we probably can. So long-term stiffness, this may not be a bad approach. We think there may be some alternates, but it's a simple way of doing it. The 0.6 is conservative, but realize you need to use the lower bound equations, those 0.4 to 0.2 EI, right? When I use it with Kuntia, that's in the code right now, if I use that, it's unconservative. So if you have a good first initial stiffness, you only use the 0.6, it's just not taking enough off for the slender, for the sustained load effect. 1.0, we felt gave really accurate short-term, or reasonable for the short-term equations that were accurate. So we think it may provide a lower bound and be a good number. It's 50% of the stiffness, but I'm going to caution here, I think further research is needed. I mean, we had a limited number of tests here sustained. It works. What we were hoping to do, as I mentioned before, is develop an analysis procedure that could predict the behavior of 30,000 columns, that we could compare to a whole family of sustained loads and then make sure what we had worked. But we haven't been able to develop that tool yet. The sustained analysis of predicting how it sustains and then goes up, we're getting close, but we're still not there where we feel comfortable with that yet. But that's the goal, so we don't have to test 30,000 columns. I mean, we want to test a range, know we're good, and then move forward. So we also did look at the short columns. I just wanted to mention something here because I mentioned I sustained for 100 days. We looked at plain, totally plain, and reinforced. No second order effects, scale of order 13. We had different eccentricities also from no eccentricity up. And we also made sure we put 50% F prime C at the compression face, always the same. So we have a similar creep was the idea. And we monitored the strain on both the compression and tension face. And we loaded these for a year. So we didn't just have 100 days, but a year. So if I take a look at that, this is plain columns. These 3 different eccentricities followed pretty well. The creep did at 50%, holding that worked pretty well. Here's reinforced. It's going to break down your strain because the steel is taking, right? The steel is shedding, the concrete shedding load into that steel. And so you see the reduction here. But if I take a look at a duration, let's say reinforced here, I'm at here about 250 microstrain, so I'm coming up now. So there is some more strain that will develop. Obviously the bulk of it's all happening here, but there is some more. So we were cognizant that we only loaded to 100. So I feel still better with a 1.0 than that 0.6 that I was mentioning here for the sustained load effect. So conclusions, this equation works really well for short-term stiffness. So this would be a good way to proceed further. The long-term stiffness of the beta DNS, and I just want to stress that, it's really only applicable for the simple equations. If you use Kuntia, that is not a good idea because accurate stiffness, it also already can be unconservative, and then I'm not going to cut it down enough by the sustained load effect. Accurate stiffness do require a higher beta. We think 1.0 is actually a good number. But again, I caution on that number. We just don't have enough yet that I feel comfortable we can put in the code at this point. Further research is really needed to define that, to make sure that we're okay. Because again, I'm not, it's one thing to say I'm doing, I don't know, say we're talking about crack control, but if I'm a little off on the cracks, and I don't want to have a column out here that we're significantly underestimating the moments that we're going to put in the code that can be used for every building that we're going to design with. So I feel very comfortable in the short-term stiffness. We could codify that tomorrow. It's just the sustain effect we have to bring in. The limit of 1.4, I didn't spend a lot of time on that. It's not needed for the brace columns. We can predict what these values are, how much moment is happening, regardless of the level. So we don't need a limit in the code for the non-sway case. I wanted to mention one thing on that. When your second order effects start to become much higher than your first order effects, I think as designers you need to start thinking about it, right? Because the slenderness, the bending of that column is causing more moment than what the primary effect is. Is that where you want to be or not? If you have very little moment, eccentricity, it's not as bad. If you have a bit of moment and you got 100 foot kips on that column or something like that, now you're getting 200 to 300 because of the second order. I mean, your sensitivity is there. So it's just something to think about. But I think we can get rid of the 1.4 for the non-sway. Let's show you some really slender columns. So look at that. I don't know. This is a precast one too. So you can see, I mean, they're using in slender columns in the precast pre-stressed world quite a bit too. So for PCI, we actually have also gotten some guidance to them. The 0.4 EI works really well too. So you can use the 0.4 EIs. We have the equations also. Those will work for the precast. So with that, I didn't go too long on the time here.
No, you did very well.
Yeah.
Any questions?
I'll open up for any questions.
Yeah.
And I hope for those of you that are instructional engineers, I didn't get way out of bounds there in terms of some of the detail. But I think you got to look at the whole thing. But people are pushing some of these columns. Yes.
When would this be applied to a code?
Well, the earliest that we're going to see something is 2019. So that's the next edition of 318 we're currently working on. And so will it make it there or not? I don't know. Again, my concern, I was ready to push it all until we have some uncertainty on the sustained load effect. And that's really the thing that would bar me back or hold me back a little from pushing it too far. I mean, in terms of getting the Kuntia out, I mean, I have SK to deal with, but y'all know SK? Any of y'all know SK? Yeah, I know. So, he has some ownership of that equation. So I'll talk to SK about that. That's another story. But I think there's some, that I think we ought to really consider of moving out. I don't think anyone's really using it. And so I don't think it's a hardship to get rid of it, but I think it can be unsafe, and that's my concern. So that is likely to happen in 2019. Whether we will have enough data to get the other part in there yet, I'm on edge about that, because it turns out 2019 sounds far away. It's actually, in code world, not that far away because of the process we have to go through with public review and the whole thing. So we need to wrap up a lot of our things within the next year in order for it to really guarantee to be in the 2019 code. The next code after that likely will be 3 years beyond, so.
Well, what
Unless
about
IBC
research?
changes their whole thing again, and they keep changing stuff. So.
Robert, what about, you need more research to, find more findings on this?
I think, yeah, we definitely, I mean, we really need
Sustained
more
load.
research on the sustained load effect. What I would like to also do, and I think I'd like to take some where I had the same column, but I sustain them at different loads. We were trying to push the columns, look at the one, we were doing a lot of things in here. I'd like to take the same column and sustain it at, 10, 30, 4, different sustained loads, because I believe that will show us how much sustained, the lower my load level, obviously I don't have as much that's happening, I believe that it will show the 1.0 is going to work beautifully, and that we can predict them all the way up essentially to final failure. And so we, had only a certain amount of, dollars to play on this. I have the frames now, all that we invested in, so I think we ought to be able to do some more. And we were trying to answer PCI. We did a lot of I didn't show those, but we did pre-stress columns. And so we were pre-stressing in the lab, getting those columns done. So I think we answered a lot of questions, but the sustained load one is still, we need to hone in. We were trying to push them as high sustained loads as we could to make sure we were safe. But in that, we lost some of the behavior things as we were trying to analyze. Said, boy, it would have been great if we would have had these to make sure we were predicting them correctly. I saw a question.
Yeah.
We're seeing a lot of super high strength concrete columns in the New York area, but I think the one real problem we're seeing, especially as they get taller and thinner, and we're having really large pieces of rebar in there. So how do you get the concrete in there?
You're gonna have to repeat the question for the back.
Yeah, I guess the question is that how do you get the concrete in when you have smaller columns and large bars inside of there that's developing? And so that's means and methods, I'm always told by my colleagues that are contractors, so let them figure it out. But no, I mean, it becomes a reality, right, as we're starting to do things, is how do you, if you're getting a network in there, and I've seen some problems in some litigation type cases where they put the bars so dang close to each other you couldn't even get concrete in between the bars, and so I think the constructability needs to be thought about as we're trying to do some of these things. But when you're going to some of the higher strength steels, 100 KSI, that could lead to a lot of these, you're going to get columns that can be shorter. So we, at the very end, because we're working with Pankow Foundation, we did a ATC study. There's an ATC report saying the next generation of codes are we're going to address 100 KSI, 120 KSI bars. Our code currently limits us to 80 KSI. There's a few things that limit you to 60 and a 75 embedded, but there's an 80 hard limit really in our code. So as we would push that to 100, what research needs to be done? We outlined, looking at every single thing, from bond to shear strength to cracking, all type of things, what needs to be done to move that to the higher strength bars. And I saw Ramon, he was involved in that effort too. And so it was kind of interesting because when we were doing that study, my student was still working this. I said, hey, everything was grade 60. Let's just throw in 100 in that. So we started to, in his dissertation report that was provided, had a little look at what needed to adjust, and just a few little things that would adjust, but in general, what we have works for the grade 100. Yeah, I'm sorry. Yeah, ATC 115. It's a free download for anybody that's interested in looking at that. You can go to ATC's site or the Pankow Foundation's.
Has this been published anywhere?
It has not been published yet, other than the report that was provided to each of our industry sponsors at this point. We are working on some journal publications, and there's a small publication of proceedings for the PCI that was down in Nashville, actually just presented a few weeks ago.
Second
It's really hot off the press right
And
now.
the slenderness, with the slenderness columns, obviously the tolerances become critical. How do these formulas take into account the
We're still
tolerances in
recommending that
construction?
stiffness of 0.75. So technically, none of this was showing the 0.75 in that EI, but that is the stiffness reduction factor for the fact that if your column is actually not constructed properly, it's a little smaller, it's going to reduce the stiffness beyond what this is going to predict. So you're taking a 3/4 hit or a quarter hit, but you're only going to account for 75% of that stiffness. And actually, with some of the equations, some of that stuff saves us, right? Because of problems that develop. Because in design, if it was built perfectly, we can predict it well, but if it's off and columns don't align correctly and you're getting eccentricities that you didn't think about, right? So that's why we have these accidental eccentricity factors in. What's actually happening right now with that 1.4 factor is many times the minimum eccentricity is what's kicking in the 1.4. So you hit this minimum eccentricity, and then when the column is actually magnifying more than that, just under minimum eccentricity. So that's where I think we can get rid of the 1.4.
Boris, there's an annual report on the table, Concrete Industry Foundation that gives a report on this research, but the total amount of pages, I think, is about 130 pages.
Yeah, it's about.
But there's a recap in
Maybe
that
more
annual
than that,
report on the research.
But if you want to contact me, I'm glad to send you the report. To anybody, just let me know. I'm glad to forward that to you. And yeah, we need to get the journal papers out on it. Unfortunately, my personal problem, I became associate dean of the College of Engineering, and so as part of that, I'm responsible for all the facilities in the college, all the finances, and all safety in the college. So with that aspect, it's taken away a little bit of my time. So.
Sure. Well, thank you, Robert.
So.
Everybody else enjoy your day, the rest of your day. That was interesting.
Sure.
I'm afraid I'm an architect, so I see all this.
Oh, that's okay. I'm working with a lot of architects.